Turning your passion into a job is easier than finding a job that matches your passion. Dear technocrats, a very good morning and welcome on behalf of IFAT College of Engineering to everyone present today. Our event for today will surely give us a lot of learning about the applications of deep neural network in drug discovery and development. It's my delight to, to be your MC today for this informative seminar. I am Rajeshwari and I'm very happy to accompanied by the charming co-MC, Professor Raj Mohan. We hope you will bargain the program we have wrinkled up for you to be fruitful and engaging. Prayer is not asking. Prayer is putting and listening with a prayer.
To kick off this morning program, we are pleased to have with us our very own Dr. P. Kanimuri, Head, Department of Computer Science and Engineering, to deliver the welcome address.
College of Engineering. On behalf of IFET College of Engineering, I take extraordinary pleasure in welcoming you all for the CSIR-sponsored one-day national seminar on application of deep neural network in drug discovery and development. I welcome our principal, Dr. G. Mahendran, whose constant support and encouragement made us achieve this milestone. My heartiest welcome to our Dean Academics, Dr. S. Matilda, who has been the catalyst and thrust of this program. My heartfelt welcome to the head R&D, Dr. Vaidyanathan, heads of various departments, professors, and faculty members. I extend a warm welcome to the coordinators of the program, Dr. K. Santan Lakshmi, Associate Professor and Head Department of Humanities and Studies, Humanities and Science, and Ms. M. Pavitra, Assistant Professor, Department of CSE. I feel happy in extending a warm welcome to all the faculty members of this program. Last but not least, a very cordial welcome to the guest speakers and participants who are here to participate in this exemplary event. I also thank the management for their ceaseless support and stimulus in organizing these kinds of programs. I wish you all good luck and may this seminar benefit all of you. Thank you.
Thank you so much, ma'am. Before we proceed to the first session, we have some general instructions. We request the participants to kindly turn off their camera and mic during the session. Participants, if you have any question during the presentation, please raise your hand or put them into the chat box. We'll bring them up at the end of the session. Please fill the feedback form that will be posted in the chat box at the end of every session.
Session 1 will be on Introduction to Deep Neural Network. It will be handled by Dr. K. Wenningston, Assistant Professor, Department of Computer Science and Engineering, NIT Srinagar, India. Now, I request Professor R. Raj Mohan to introduce our vibrant resource person.
It gives me immense pleasure in introducing our resource person, Dr. K. Wenningston, Assistant Professor, Department of CSE, NIT Srinagar, to the gathering. Dr. K. Wenningston is currently serving as Assistant Professor in the Department of Computer Science and Engineering at National Institute of Technology, Srinagar, Jammu and Kashmir. He received his PhD in Computer Science Engineering from Anna University, Chennai in 2015. His area of expertise includes computer vision, natural language processing, group modeling of web users, topic modeling, personalized web document ranking, image re-ranking, and computational intelligence. His current interests are applications of deep learning in the area of image understanding, text summarization, social network data analysis, He has several international conferences and journal publications to his credit. I thank him for providing his gracious presence to join us today. Now, I request our resource person, Dr. K. Winningston, to take over the session. Over to you, sir.
Very good morning to one and all. I thank the organizers for having invited part of this CSIR sponsored seminar on applications of deep neural network in drug discovery. I think I can proceed with the session. Can I share my screen?
Yes, sir, you'll be able to share your screen, sir.
Yeah. Okay. I hope my presentation is visible. Let's get
Yes,
started.
sir.
The topic for this presentation is going to be on applications of deep learning in drug discovery. The agenda of the presentation would go like this. So first, let me introduce you what learning is all about, and then we shall get into some of the preliminary concepts of deep learning, and then we shall slowly move into the drug discovery, the task of drug discovery, and let's try to orient drug discovery with deep learning. Okay? And I would like to spend more time in explaining this deep learning preliminaries, and then we shall move on to some use cases under the umbrella of drug discovery. So that's the idea of this 2-hour presentation. Yes, first let us understand what learning is all about. So learning is possible only given data. Okay? So learning is essentially all about data. So given data, so we may try to learn something. And so what are we essentially going to learn from data? Say, for example, assume that we have a data which is in the tabular form like this. So kindly bear with my scribblings. So I'm using mouse to make some scribblings on the screen. Okay. So assume that this is how my data looks like. Okay. I have two things in my data. One is X part, which defines the features of the data, and then I have the Y part. So this let me better take an example so that these x's and y will be much more clear. Let me consider, let's say, the heart disease prediction data set. So there is a data set for heart disease prediction. Okay. So now these are some of the features. Okay. So the x1 may denote the age of the patient, and then x2 may denote whether they have experienced chest pain in the past or not. Okay. And then the X3 would denote some other feature corresponding to this heart disease. Okay. Finally, we have Y label. So Y would be either 0 or 1. So in case if this particular patient has heart disease, then this entry would be 1. In case if Y value equal to 0, which means that this patient with some feature values and who is not experienced heart disease, so who is not diagnosed with heart disease, we can put it that way. That we have reasonably bigger size of data, and this X could be even in terms of hundreds. Okay. So for example, I've just taken only 3 features here, and when we work on some standard data set, probably we would have hundreds of X's. Okay. So X1, the X's may be ranging from X1 to, let's say, X100. Okay. And then finally we have this Y label, which denotes the class to which this particular patient goes. So every row in this data set denotes a patient health record, and then this Y label corresponds to the corresponds whether the patient is diagnosed with heart disease or not. Okay, so this is the data which is observed in the past, and we can make use of this data so as to learn something from this data, so as to use it for the future patients. Okay, for example, so given a new patient, and if we want to check if the patient will be diagnosed with heart, what is the chances that the patient may be diagnosed with heart disease? In this case, it is a binary value here. So we are just interested in whether the patient will be diagnosed with heart disease or not. You can also look at the same problem in the other aspect, and you may also be interested in finding out some probability value which may denote the chances of being diagnosed with heart disease or not. So now, so given data which contains both X part and Y part, and what are we really interested in? So looking at this data of this form, X's and Y, So given x's and y, and we want to find out the relationship between x and y. So this relationship, the relationship between x's and y could be written in terms of, let's say, some function of all x's. So in case if you have three x's, then it's going to be a function of x1, x2, and x3, and with some parameters. So it would even include some parameters, and let me just call it p here. Right. So this is the function which we essentially want to learn. Okay. Essentially, just by looking at this data, in case if the data is a two-dimensional data, probably if data has only two features in it, let's say x1 and x2. So probably it would be easy for us to visualize the data, and we can try to figure out, or we can make some blind case. What is the function which defines the relationship between x1, x2 with y. So y maybe, let's say, some function. In this case, but let me take some other set of data points. So for simple case, let me take few data points. So all these yellow dots are the data points. So in case if these are the data points, then it's very obvious that the function is going to be like a line, so which passes through all these data points, and this is the function f which I'm interested in. So this is the function which I'm interested in, which is going to be a function of x1 and x2, and I call this function as, let's say, y. So in case if it is a true relationship, because the true value is already given as part of your data, so that's why we call it y. And if you our idea is to approximate this function, because we do not know any, we don't have any clue on this function f, and we are trying to approximate it with the help of this data set. Okay, so we call this portion of data set as a training data set, and we use this training data set in order to come up with an approximation. Approximation is a function which defines the relationship between x's and y. Okay, so since we are trying to approximate it, so we essentially refer to this function that we are trying to approximate as y hat. So y hat is now we have y, which is part of your data, and we have already approximated the function y hat, and this function will also guess some output, and then once we get the predicted output, which is y hat, and we have the actual output y, then we can compare these two, and we can see how good this function f is. So in case if the difference between y and y hat is high, probably we should fine tune this function. So any function in mathematics will also come with will also come with a set of parameters. And in this case, let us assume to be over a set of parameters denoted by p. Okay? So by adjusting this p, so we will be able to minimize, or will be able to minimize the difference between y and y hat. Okay? So we would do it we would do it by doing several trials and experimentations, and then finally we would bring down the difference between y and y hat to as minimum as possible. So this is what all about learning. So guessing function is not a learning. So adjusting this parameter value is what learning. So by adjusting this parameter value, so we try to better approximate the relationship between x and y. And in case of two-dimensional data, so this task is going to be very simple. The learning is going to be very simple. And if we have just two dimensions in our data, the number of parameters that we are dealing with is also going to be very less in number. So in case if you are working with multi-dimensional data, then the number of parameters will be enormous. Okay? So in that case, so we require a systematic way of fine-tuning the parameter values so as to approximate this function better, which explains the relationship between x and y. So that is what all about learning. Okay? So this machine learning or deep learning, so where we frequently use this term learning, where computers actually creates models of system behavior based on the historical data. So for training any of the model, if you want to learn something, you must have the historical data. So in this case, I have taken the historical data about several patients. So in order to learn something from it. Okay, so that if I learn something from it, then probably I can make use of this model, or I can make use of this function which I have approximated, which is y hat, so as to make predictions on some unseen patients. So when some unseen patient comes, probably you could from the patient's medical records, so you could gather what is X1, what is X2, what is X3, and so on and so forth up to X100. So once you gather values of those features about a patient, who is not involved in the process of learning, then probably you can make a prediction. So whether the patient will be diagnosed with heart disease or not. Then, and if you want to come up with a better model or a function, so this model and function could be interchangeably used. So whenever I say model, I mean the function which I'm trying to approximate, to explain the relationship between x's and y's. So now, as we have more and more information, so if we have denser information in our data, then probably we'll be able to come up with a better model. So that is one key thing. So that's the reason why any machine learning or deep learning related tasks, generally we work with good amount of data. So if you don't have much data, you will not be able to learn much from it. And moreover, machines actually do not have capability to learn by itself. So we're supposed to make a machine to learn from data. Okay? So machine actually learns from what we essentially teach them. Okay? So in all these aspects, so we as a human being play a vital role than a machine. Probably machine would help us to figure out the possible values for these parameters, but these functions, it is in our hands that we are supposed to define what is the function which must be tried out. So again, as I told you, in case of 2D, just by plotting or visualizing the data, we could somehow guess the function that we wanted to try out. But in case of multi-dimensional scenario, in case if we deal with thousands or 2,000 features, then it will be very difficult, especially in the case of drug discovery applications. So we would actually be working with a lot of chemical components where which could be represented well by several numerous attributes. So we would actually be dealing with thousands and thousands of attributes. In that case, we may not be able to guess. First of all, we may not be able to visualize at all. So even visualization itself is a difficult task. So if you're not able to visualize, then it's very difficult to understand the underlying pattern of relationship that exists between x's and y's. Okay, x's and y. Right. Then these are several applications where learning plays a vital role. So let me just briefly put forth what classification is all about. So classification, the task that we have discussed just before is an example of a classification task. So here we classify every patient into either of these two categories. So whether the patient will be diagnosed with heart disease or not. So in case if the patient is diagnosed, then the corresponding y value will be 1. In case if the patient is not diagnosed, the corresponding value will be 0. So it's a simple binary classification problem. We are interested in only one of the two classes. And then we have similarly, you could even think of multi-class classification aspect, especially in the context of drug discovery. Let me talk about that bit later. So the most of the learning problems that we see in the context of drug discovery, and most of them are actually multi-class classification problems. Okay? Right. And then coming to anomaly detection. So I've just listed very few here, and the list actually goes very long. The anomaly detection is all about maybe given an image, so you may be interested in finding out whether there is an anomaly present in this image or not. Okay? This image could be, let's say, a chest CT scan image or X-ray image. Okay? So assume that this is a chest X-ray image given to you, and you want to figure out whether there is an anomaly present in this X-ray image or not. Okay? Again, in order to train such anomaly detection model, so you require a lot of images which are labeled, which means probably if you possibly have let's say 500 images which are labeled as yes, which means there is an anomaly present in these 500 chest X-ray images. And then similarly, you should also have another 500 images which does not have any anomaly. So probably by using the data containing 1000 images, where 500 off of the data are with anomaly and off of the data are without anomaly. So in that case, you could essentially come up with some function of this kind, function of this kind, uh, which is going to be of all the features present in this image. Okay? And coming to an image, we know every pixel is a feature. Okay? So in case if the size of this image is, let's say, 30 cross 30, then we are actually dealing with 900 features. Okay? So the x1 is going to be, let's say, the pixel at the top left corner, and then x2 could be the pixel next to it to the right, and then the pixel next to it to the right could be x3, and so on and so forth. Okay? So you can read the pixels, row by row, and then you can appropriately have features from x1, x2, and so on and so forth up to x900. Okay, this is how we essentially represent features from an image. Okay. Again, coming to an image data. So here we are actually working on high dimensional data in the case of image related tasks. So definitely, plotting these pixel values and then figuring out what could be the function which could better approximate the relationship between x and y. So it's a very tedious task, and moreover, we'll not be able to do it. So in that case, we will have to figure out, we will have to try out several configurations. Whenever I say configurations, I mean different functions. So we may have to try out different set of functions, and then again try to predict y hat, and then try to compare it with its actual label, and then whichever function which minimizes the difference between y and y hat, and that's the function that we're interested in. Probably once you figure out such function, then by adjusting its parameter value, then you could better represent the relationship between x's and y. So that's about anomaly detection, and you could also think about various other healthcare related images as well. Given an eye fundus image, probably you could check out whether there is an anomaly present in the image. And then thirdly, we have object identification. For example, again, it is again an image related task. So given an image, you may be interested in learning a model so as to identify an object present in the image. So a given image may contain a car object in it. So you may be interested in learning a system or learning a model or learning a function in order to check, in order to identify what object is present in it. For example, in case if there is a car in the given input image, and your expected output is actually a car. Okay? So we want to assume that you are interested in identifying, let's say, 4 different objects. Okay? So in that case, this object identification task becomes a 4-class classification task. Let's say we are interested in finding out whether there is a car, or let's say dog, or cat, or some other object. Let's say book or something. Right. So now, given an image, you must have a good number of images explaining each of these classes. So you must have in your data set, let's say, thousands of images which has car in it, and thousands of images which has dog in it, and then thousands of images which has cat in it, and then thousands of images which has book in it. Okay? And then you try to come up with a learning model. So once you come up with such a learning model or a function, then you can make use of that approximated function in order to identify objects in the unseen images. So given an unseen image, then you may figure out what is the probability that there is a car present in it, or what is the probability that the dog present in it, and then what is the probability that cat or book image or object present in the given image. So this is also a kind of classification task, and then even anomaly detection is also a kind of classification task. So as we have seen before, it's going to be a binary class classification problem, because we are interested in checking whether there is an anomaly present or not. So it's going to be a 2-class classification problem, whereas depends on the number of objects that you wanted to identify from an image. So this object identification task will become a multi-class classification problem. So in case if you are interested in only these 4 categories, car, dog, cat, and then book, then it becomes 4-class classification problem. So in case if you are interested in 10 objects, then it becomes 10-class classification. And then we have prediction and forecasting. Okay? And in case of classification tasks, we are actually interested in labels. So we are actually interested in some categorical value, which could be either yes or no, or 0 or 1, or it could be either car or dog or cat or book. Those are going to be well defined categories. Whereas if your task requires, you want to let's say the output is not categorical. If the output is continuous, if the output is real value, then it becomes then such tasks are going to be referred as prediction or forecasting. Okay? So you may try to predict, let's say, house price. So given some features like the size of the house, and the location of the house, and then what is the crime rate at the locality, and so on and so forth, and then the number of floors, number of stories in the building, and and so on. That depends on the the width of the road, and so on and so forth. So probably you could figure out what is going to be uh, the price of the house. So again, in order to train such model, you require some past data. Okay? So you must have some historical data, and you can do some learning on them, and then you can come up with some approximation, and you can use this approximation, let's say f hat, an approximated function, because there is a true relationship which exists between x and y, which is denoted by f. And since we are trying to approximate this function by learning, I call it f hat. So once you get f hat, then you can substitute the values of the features, and then you can find out what is going to be the expected value of the house. So in that particular locality. So that's about the prediction and forecasting. So again, coming to forecasting, so you may be interested in forecasting. So what's going to be the share price tomorrow, or what's going to be the price of the stock probably after 1 month or after 2 months. If you want to forecast it well in advance, then that actually comes under the type of data called time series data. And in case of prediction, we are interested in real values, and even in case of forecasting, we are interested in real values. But the data that we are going to use for forecasting is going to be time series data. Okay? So every data point in the data set will be associated with some timestamp. Right. And then we have another class of tasks called generation. Okay? We may want to generate something. Again, in the context of drug discovery, this generate we have something known as generative model in the context of deep neural network, which is widely being used. Okay? So you could find some recent survey papers, literature survey, which talks about generative models in drug discovery. So again, let me put forth a few more points on these generative models in the later slides. And earlier, even currently, the generation is all about working with some sort of sequence data. I raise my screen. So generation is all about, let's say, you have thousands of tweets written by our Prime Minister. Assume that our Prime Minister Narendra Modi ji has written, let's say, thousands of tweets. Now, we want to come up with a learning model which can automatically generate a tweet for an occasion which is very much related, very much close to the pattern that the Prime Minister of India follows. Okay? So everybody will have some different writing skill, right? So even if you consider your own self, so you will have way of writing tweets or way of writing messages in social media. Okay, so probably you could gather all your own data, and then you can come up with a model, come up with a generative model, so which can help you to generate tweets for you, maybe for a given occasion. So this automated system may help you to generate tweets. So which is people should feel that will essentially feel that the tweet was actually written by you, not by an automated system. Okay? So such applications are known as generation tasks. So again, similarly, given set of paintings, yeah, again the system automatically can come up with the new paintings, so which exhibits the characteristics of a particular painting. So even though it is automatically generated, but it should give an appeal that the painting is actually done by a human being. So it should be that close. Yeah, again, there are several successful generative models are available in practice and which are being widely used for several tasks. And then language processing. And when I say language processing, I mean every task which are related to text. Again, one such example is, you can think about next word prediction. As you type something in Google search engine, so what actually it does, so it actually gives you some sort of recommendations or sort of some sort of help tips. So as you start typing, so it also on the other hand it gives you some sort of recommendation. So what it actually guess what would you type probably next. So so that it helps you, type your query faster. Okay. So such type of tasks are known as sequence learning tasks. So where there is a model in place which is keep learning as well as it is trained to find out the most probable word that user might type next. Okay. So those types, there are several types of language processing applications are there. Even you could even combine language processing with classification, language processing with generation, and so on. Generation automatically is a kind of language processing task. Similarly, you could also think of a classification task which uses text. So maybe given a review text, and you may rate it. Okay? So in the scale of 1 to 5. So given a tweet, in case if the tweet is a very positive tweet, probably you could come up with some model so which could automatically assign some rating value as 5. So in case if a product has received a very worst review from a customer, probably then it could automatically assign a rating of 1. So again, it's a kind of classification task for which input is going to be in the form of text processing tasks. So that's about learning. So from this, we understood that we are interested in approximating the relationship x and y because we do not know the relationship that x between x and y, and so that's why we are trying to approximate the relationship. So the approximated relationship is going to be defined as f hat, and the outcome which is going to be given by this f hat is going to be given by y hat. Okay? So since we have historical data with us, then it will be easy for us to actually compare this y hat with y. Okay? Because in order to learn this function, so we will actually make use of this historical data. Probably once you once you figure out this approximation, probably you could simply ignore this y column and keep it aside, and then take all these values from this x part and then give it to this y hat, and it would make some prediction that is y hat, and you now compare this y hat with the given y and check if how close this y hat is. Again, do it across across the majority of data points in your data set. In case if 1,000 times, let's say the prediction is 900 times correct. So in that case, you can be sure that it was 90% right. Okay? So if you are okay with 90% right function, then you can stick to this function. At the same time, you cannot stick to this function forever. So it is going to be an iterative process, and you will have to keep updating this approximation. As and when you get to accumulate more and more historical data, then it is good to revise this approximation, and then you reconfigure it. Okay? Right. And coming to the preliminaries of deep learning. Okay. So these are some of the things that we essentially come across if you take up any of the ML or deep learning related projects. So the first thing that you require is data. So data is the most essential thing. As I told you before, learning happens over data. So, and moreover, data are available everywhere. Moreover, we don't lag in data. There are several online repositories available, and they provide data free of cost. And most of the data that we are in need currently, all of them are actually available, open. Moreover, it's freely downloadable. Probably I would like to reiterate, and there is a portal called Kaggle. Even the two of the data sets which I have explored for this task are actually from the Kaggle portal. Even for the drug discovery related tasks, the data set is provided by Kaggle. It's reasonably big data, which you could make use of, and you can try applying some deep learning techniques over it, and you can try to see some interesting outputs from it. And coming to data, okay, and moreover, because data are available everywhere, it doesn't mean that you can definitely apply some ML and DL over it. Okay? It doesn't mean that we can definitely apply machine learning or deep learning on any data that we have. Okay? So in order to apply machine learning or deep learning, so we actually need some specific type of data. Okay? For example, as we have seen in the previous slide, and every data that you're going to talk about, all of them are actually called as supervised learning algorithms. All these tasks are actually supervised learning tasks, which means for a supervised learning task, we require both the X part as well as the Y part, which means we require the set of features along with its label. So only then we'll be able to perform. Okay? So even in the case of forecasting, if you're interested in forecasting, let's say a share price probably next week or next month, so again you must have historical data. Okay? So you must have historical data, let's say for the past 1 year data, and assume that at every time second, at every second, the price of the stock is going to be recorded in the data set. Maybe for a period of year time, then you could imagine how big the data is going to be. Okay? And in this, probably you will have two columns. So one is the timestamp at which the stock price is stored, and then the actual price of the stock. So this will be available for all the entries in the data set. So in this case, probably this timestamp is going to be, let's say, the X part, and then the actual share price is going to be Y part. Again, coming to anomaly detection, you must be having set of images along with its labels. So you may have 500 images having anomalies for which the label will be 1, and you may have another set of 500 images for which label is going to be 0, which denotes there is no anomaly existing in those images. Okay? So again, coming to object identifications, again given an image, so you must have what is the object which is present in this image. So you must have it for the number of objects that you deal with. So data should be in a prescribed form so that you'll be able to apply machine learning or deep learning. Okay? To be precise, so probably the data should be in the form of X's and Y's. So any data that you have, so you must be able to represent it in terms of X's and Y's. So you must have set of features called X, and then you must have its corresponding label. So only when you have a data of this kind, then you will be able to learn something from it. So what are we trying to learn? We are actually trying to learn the relationship which exists between X's and Y. So that's the major thing that we are interested in on this type of data. And then coming to tasks. Again, tasks. So we're supposed to define the task that we're interested in. So given a data, so we must also define the task that we're interested in. So again, I have another slide where I have different data sets which are primarily used for drug discovery, and then I have also listed several tasks which could be possibly performed on that data. And these are some of the tasks that we may be interested in. Okay, a task could be a classification task, or it could be a regression task, or it could be a forecasting task, or it could be a generation task, and so on and so forth. And then thirdly, we need to think about models. So models is what known as the function that you're trying to approximate. So since we do not know the actual function which defines the relationship between X's and Y, so we're supposed to approximate it. Okay? So where from this function comes, okay? Again, different machine learning algorithms will give a different interpretation for this model. And since our focus is on deep learning, so I'm going to show you, how this function f hat is going to be modeled by using some flavor of neural network. Okay? So every neural network that we see could be termed as a kind of function. So then let me put forth, and I will come to this slide. So this is a kind of neural network. If you have already have some base on think that it is a neural network, and where we have we feed a set of inputs to this neural network, and then we get some output at this layer, and then somewhere in middle we have different layers, and then something is happening. So a lot of computations are being done here, in order to arrive at this output, which is y hat. Now, what is this model? And this entire neural network is what the model. So this entire neural network is what is trying to give us the function f hat, which tries to approximate the relationship between x's and y. Okay? Maybe if I try out another configuration, let's say without this neuron, then that becomes another f hat. So let me call that f hat as actually f no, one hat. So which is again a function over all x's and then y. Probably if I happen to remove this complete layer, I just need only one hidden layer. I don't want two hidden layers. So again, what is left over is again a neural network, which could again approximate to some extent, which we may say it is f2 hat, which is again function over all x's and then y and so on. So since we do not know what is the true relationship which exists between x's and y, so we need to try out different configurations. So it's going to be a trial and error kind of way, in order to figure out the best function or best approximation which explains the relationship between x's and y. There is no systematic guide for us to decide the number of neurons with several layers in the deep neural network. Okay, so it is completely up to us, and we supposed to do a lot of trial and work activity at our side. Okay, so that we can bring down the gap between y and y hat. Again, in this context, there are several well-tested models are already present, such as we have something known as convolutional neural network (RNN). So we have different flavors of CNNs, we have different flavors of RNNs, we have different flavors of LSTMs, and so on. Okay, so different people and different companies have proposed their own version of deep neural network frameworks, which will try to solve most of the tasks. Probably if you take a version of CNN, let's say there is something known as AlexNet. There is something known as AlexNet, which is a kind of which is one of the CNN architectures, and probably by using AlexNet, you'll be able to solve several image related classification tasks. So probably you can instead of coming up with your own deep neural network, in order to approximate the relationship between x and y, what you could do, you could start with some of the standard architecture, which is already in place. For example, you can start working with AlexNet and try to see if the effectiveness of this AlexNet on your data. Maybe in case if it is not good, probably you can fine tune this AlexNet. You try changing some of the configurations in this AlexNet, because AlexNet is a standard architecture of CNN, and probably you could add one more layer to it, or you can delete or remove some layer from the existing AlexNet, and try if you are able to bring down the difference between y and y hat. So probably that's the way how you can essentially think about models. Okay, and then model most of the time is going to be task specific. It depends on the task that you have, so you can appropriately choose the right model. But, in the case of AlexNet, AlexNet is actually defined. AlexNet is a CNN configuration which is available for object classification task. So given an image, so it will tell you, what is the probability that this image contains a car or dog or cat or book or some other object and so on, right? And then so as I told you before, so once we have data, we can apply this model on this data, and as you apply a model on this data, so you'll be able to compute this y hat. So y hat is going to be going to be the output which is predicted by the model that you are experimenting now. Okay, so assume that this is one of the models that you're trying out. So as you try this particular deep neural network model, let me tell you why do I call this as deep neural network. Now if you look at it, so it takes all the inputs. Let's say in this case it takes 13 features from x1 to x13, and then it performs a lot of computations on the go, and then finally it gives us the prediction, which is y hat. And now since we are working on supervised learning task, and the corresponding maybe the data point that we are experimenting right now, for which the known label would also be present as part of your data. Since it is already present, you can now compare y and y hat. How can we compare it? So there comes the notion of loss function. And loss function will give you a way to compare or to find out the difference between y and y hat. And let's say for some data points, the actual label given is like this 11010. So assume that this is a heart disease data set, and this Y column denotes, in case if it is 1, it denotes that the patient is diagnosed with heart disease. In case if it is 0, the patient is not diagnosed with heart disease, okay, for a given axis. Now, once you choose a function, once you choose a model, so the model would also make a prediction. So the prediction made by the model is denoted by y hat, and now assume that the y hat goes like this. Okay? So it predicted the first data point correctly, and then it predicted second data point wrongly, third data point wrongly, and then fourth correctly, and fifth correctly. So now you could simply find out the difference between these two. So there are several ways by which you can compare y and y hat. So again, it's going to be task specific. So in case if it is a binary classification task, so you could simply use the square difference. So you just simply find out the square difference between y and y hat. Okay. So for these 5 data points, you just find out the square difference. So square difference could be computed this way. It's going to be, or you could even compute the sum of square difference. So where I is going to be from 1 to 5, because I just want to find out among these 5 instances how many instances are actually wrongly predicted by the model. Okay, so it's going to be computed as y, let's say yi minus yi hat, and then take the square of it. So the reason why we take square here, because in this case, what would happen? This 1 minus 1 would give us 0. Okay, 1 minus 1 would give us 0, and 1 minus 0 would give us 1, and 0 minus 1 would actually give us minus 1. So we just want to get rid of this minus notation here. That's the reason why we take square here. And moreover, so any loss function, again we have well-defined loss functions which are very frequently used in the context of deep neural network or deep learning. However, you can also think of your own loss function. Okay? So in case if you want to figure out your own loss function, so one thing that you need to think about, that is the loss function must be differentiable. In case if the loss function is not differentiable, then you may not be use such loss function in the context of deep neural network. Okay? That is one thing. So this is one some of the square differences. It is one of the loss functions, so which is differentiable. So you can use this in the context of deep neural. So now as you apply this, so you would get 0 in case of the first one. So 0 plus 1 minus 0, and you are moreover taking square, so it is still going to be 1, and then plus 0 minus 1 again whole square, so which will again give you plus 1, and then here it's going to be 0, it's going to be 0. Now if you find sum of all this, then the sum is going to be 2. So this number 2 denotes that among these 5 instances that we have taken to compare y and y hat, so 2 of them are actually wrongly predicted by the model. So now the accuracy of the model is actually only 3 by 5, so which is almost 60%. So the model, the configuration of your model which you are experimenting currently is only 60% accurate, which means, so it makes 2 data points, it is actually misclassifying 2 data points among 5. So the accuracy is just 60%. I should not actually use the term accuracy at this point, and it makes some error. So the unit of error is actually something like this here. So 2 is a kind of error. And what is the ideal value for this error or the loss? The ideal value for this error is going to be some value which is very close to 0. Okay? So 2 is something which is not so close to 0. So we should not be happy about this model. We should not be happy about this model. So we're supposed to fine tune the model. Okay? So how can we fine tune the model? Again, there comes the notion of learning algorithms. So learning algorithms will help us to fine tune the model. So as I told you before, so the function that we are trying to approximate is going to be of function over all the x values. So it's going to be a function of all the x values, and this function is also going to come up with some parameters p. And we may initially start with some random configuration for these parameters based on the number of parameters that are involved in your model. So you could actually start with some random configuration initially. As you have a random configuration initially for this parameters, then again you'll be still be able to compute y hat. And in case if the difference between y and y hat is too much, then probably you should revise this parameters. So how can we revise the parameter values? That's by using learning algorithms. So we have several successful learning algorithms which are being widely used in the context of deep neural network. And let me list out some of them. And the very primary version of learning algorithm is called gradient descent learning algorithm. Gradient descent, and there are several flavors of gradient descents. So we have something known as accelerated gradient descent. We have momentum-based gradient descent. We have stochastic gradient descent, and so on and so forth. Okay. Actually, a stochastic gradient descent is not a type. Actually, the gradient descent and momentum-based gradient descent, then the accelerated gradient descent, or the gradient descent algorithms, and you can use these learning algorithms in different configuration, which means we have something known as batch gradient descent. We have batch gradient descent, and then the stochastic gradient descent, and then mini batch gradient descent. Batch, mini batch, stochastic. Okay, so we can have a we can have a standard gradient descent, which could be configured by just by having batch gradient descent or stochastic gradient descent or mini batch gradient descent. So in case you are not happy with gradient descent, you wanted to go with momentum based gradient descent. So again, you could implement it as either batch momentum based gradient descent or stochastic momentum based gradient descent or mini batch momentum based gradient descent. Similarly, again, accelerated gradient descent, again, it could be implemented as either batch accelerated gradient descent or stochastic accelerated gradient descent or mini batch accelerated gradient descent and so on. And then we have something known as adaptive gradient descent as well. So we have something known as adaptive gradient descent, and we call it AdaGrad. So we have something known as AdaGrad. These are some of the learning algorithms which are most widely used in deep learning applications. So AdaGrad, and maybe something known as RMS prop. So these AdaGrad and RMS props are actually being widely used currently. Okay. Again, these are all actually an extension from the earlier versions of gradient descent. Again, let me not get into details of what batch is all about, stochastic, mini batch, and all that. So these are the ways. These three are the different ways by which the updates to parameter takes place. Yeah, how frequently the updates to this parameter takes place, whether by looking at the entire training data and then you update the parameter, or you just look at only a portion of data set and then update this parameter value, or you update it for every data point. So at every data point that you are examining, you immediately update the weight for the next data point, and so on and so forth. So that is actually called stochastic gradient descent. But most widely used configuration is mini batch gradient descent. So and the mini batch should be decided in terms of something in multiples of 2. Okay? So that's the standard configuration. Most of the deep learning related code that you download from internet, and in most of the implementations, you could observe that they prefer to use this mini batch, some version of gradient descent, with the size of the batch being something in powers of 2. So it could be either 32 or 64 or 128, so that it would be more comfortable when it works with GPU CPU kind of machines, because computer is generally comfortable with anything which is in multiples of 2. So that's the reason why the size of the batch is being decided to be something in multiples of 2. So the better the learning algorithm, so the better the convergence will be. Okay? For example, if the learning algorithm is good, maybe with very few iterations. So in the context of deep learning, we call it epoch. With very few number of epochs, you will be able to converge your learning algorithm, which means you would be able to decide the right configuration for this parameter. So in case if your learning algorithm is not good, which may take several thousands of epochs. Maybe if you use gradient descent, probably assume that it takes 1000 epochs so as to bring down the loss to, let's say, some value which is close to zero. Maybe on the other hand, if you use AdaGrad, probably you would be able to converge the right set of parameters with a matter of just 10 epoch. So that's the way by which you can actually compare the effectiveness of these learning algorithms. So how one learning algorithm is going to be better than the other learning algorithm? So the rate of conversion, the speed at which the algorithm converges with the set of the right values for the parameter. That's the criteria with which you can actually evaluate the algorithm. But anyhow, a learning algorithm. Actually, no, our idea is not to evaluate the learning algorithm. So in case we have only several tens of algorithms, tens of learning algorithms which are most widely frequently used in the context of deep learning. You can practice all of them. You just run your algorithm, run different learning algorithms on your data for the task that you have at hand, and then you see which one is actually converging faster. So you just pick up the one which converges the right values for the parameters faster. So that's the that's going to be the right choice of the learning algorithm that you can essentially pick up. And once you completely run your learning algorithm, so you just decided to have some set of parameter values. So that's the parameter values that you are going to make use in order to test your model with some unseen data. So there comes the notion of evaluation. So finally you take, that's the reason why any machine learning, deep learning task, so we would actually divide the data into two parts. So one part is being trained part. Let's say if this is our data, so we would actually divide the data into two part, and one part we would call it train part, the other part we would call it test part. Okay, and sometimes we would even divide it into three parts. So we would call one part as training, the other part is testing, the other part is validation, because here we have a step called fine tuning the parameters. Right, that's the responsibility of the learning algorithm to fine tune the parameter values. Then again, we have something known as hyperparameters. So the parameters of the function is what learned by learning algorithm, and we have some other allied parameters. So we call them hyperparameters. Okay, in the context of deep neural network, some of the hyperparameters are the number of hidden layers that we can have. Okay? So in this configuration, in this simple configuration, we have two hidden layers. So the number of hidden layers is one of the hyperparameters. So who knows? No, I should just stick to only two hidden layers. Why not three? Or why not just one? Or why not 10? Why not 20? We will have to experiment it. Yeah. So we don't have any formal guide available in order to decide the number of hidden layers. So given the data and given the task, okay. So no one can actually guide you, towards choosing the number of hidden layers for your neural network configuration. Okay. So that is one hyperparameter. So the reason why we call it hyperparameter, because hyperparameter actually does not depend on the data. So anything that depends on the data are actually called parameters, and the hyperparameters are actually hyperparameters does not actually depend on the data, okay? Such as the number of hidden layers, and then the number of neurons in every hidden layer, and then the choice of learning algorithm. So why should it be AdaGrad? Why not RMS block? Again, we have various choices. So why just mini batch? Once it is successful, we know it, but maybe for the task and data that you have, the stochastic gradient descent may work better. Who knows? Okay, so unless you experiment it on, you will not be able to blindly say that with mini batch, because it worked for hundreds of applications. So you cannot believe that it would still work for your application. So those type of informal guesses in the context of deep learning application will not work out better. Yeah. So that's why you will have to implement the various choices. Similarly, why should you, stick to this sum of square differences? So there are other loss functions as well. So why don't you choose to use other loss functions as well? And then again coming to other choices, such as we use something known as activation functions at every neuron in the deep neural network configuration. So again, we have several choices for activation functions. Okay. So we have some of the activation functions such as sigmoid is one of the activation functions, and then we have TANH, we have ReLU, we have leaky ReLU. Okay. So we have several choices for activation functions as well. So the reason why we apply activation functions on a neuron in any deep neural network configuration is that we are actually interested in finding out some non-linear relationships. So as I told you before, in case if the data is 2D, probably if you do the visualization, so you'll be able to guess whether you are interested in figuring out or you're interested in approximating the linear relationship or non-linear relationship, because the line is a linear relationship, as you know, right? So in case if data points are like this, so in case if the data points looks like this, in case if the data point looks like this, so something like this. So here it is very clear that again the data is still two-dimensional, but here the relationship is not line, which means by line you will not be able to explain the relationship between x and y. Okay, so the true function here is actually something like this type. It's non-linear. So if you try out any number of linear functions like a line, so you will never be able to converge. Okay, so your learning algorithm will never be able to converge, even if you run it for 1,000 epochs or 2,000 or 5,000 or 10,000 epochs. Okay, so unless you figure out some non-linearity as part of your deep neural network, you will not be able to converge. Okay? So now there comes the notion of activation functions. Okay? Activation functions can be used in order to introduce non-linearity. Right. So trying out all these other data independent parameters such as hyperparameters, again again we're supposed to do that in order to stick to the right configuration for our deep neural network model. Right. So again you can for that purpose we actually have this validation set. Okay? But it's up to you to decide. Not mandatory that you must have validation set, because if you know the configurations okay, if you assume that somebody has guided you and has given you right set of configurations in terms of number of hidden layers to be used, and the number of neurons to be used at every hidden layer, and then the choice of activation function, the choice of initialization methods, choice of learning algorithm. So assume that somebody has guided you very well. In that case, you can completely skip this hyperparameter tuning. Okay, but in most of the deep learning applications, you cannot expect any such universal guide who can help you to choose who can help you to choose the best loss function or best activation function or best learning algorithm and so on. Okay, so it's a good practice to even have the validation set and use this validation set in order to fine tune the hyperparameters. Okay, so these are some of the preliminary things required for any sort of learning. So whether you are going to use machine learning or you are going to use deep learning. So let me quickly even talk about this. Extend it to 3 hidden layers or 4 or 5 or 6 or 10 and so on. Okay? So if you have more than one hidden layer, that is one way by which we say or we call it a deep neural network. So not only CNNs or RNNs are deep neural network. So even a simple neural network containing more than one hidden layer could be called as deep neural network by definition. Right. So here we have two neurons at the output layer. So we can say that this neural network configuration is tried out for a binary classification problem. And coming to the number of inputs you see, which are fed to this neural network configuration. So here we have 13 features, which means we have 13 input values. So you can be sure that we are actually working on a data which contains 13 features in it. Okay, so this X1 may be the age of the patient, and then X2 may be whether they've experienced a chest pain in the past or not, and then the third feature may be about age, and then the X4 may be whether what the medications that they have practiced in the earlier days, and so on and so forth. Okay, right, and we have been talking about the standardization of input, and so the range of values of different input features should not bias or should not dominate the other features. So whereas the range of age values are going to be higher compared to the range of gender. So gender is going to try out only three possible values, which may be 0, 1 or 2. Whereas age will have a range of values starting from 0 to 100. Okay? That's the valid age range that we could consider. Again, no age, because age feature has higher range of values, it should not dominate the other attributes present in the data set. Every feature in the data set should be given equal importance. Okay? So at the time of feeding the input to the neural network, so you don't apply any sort of bias on those input values. Which means based on the value of the feature, no, it should not get any specific importance over other features in the input. Okay, let the neural network define that. So as you run more and more epoch, in the process of learning the parameters, let the neural network, let the learning algorithm provide importance to each of these features, by changing the weight value associated to each of these inputs. But we should not do it at the time of feeding the input. So that's the point which I wanted to make it clear at this point. And that's the reason why standardization is important. So again, coming to standardization, just give me a second. Sorry for the interruption. So, if you have any queries at this point, probably you can ask me. Because of the disconnection, I lost the chat window. I did not see were there any queries typed in the chat window. So, if you have any queries on the terminologies end, probably you can ask me now, because we are going to spend very least amount of time on drug discovery, because even drug discovery is something which is new for me. But as I told you before, as long as you have data in the prescribed format, no, you can definitely apply deep learning or machine learning stuff, whatever. Okay, as long as you have clear-cut data which contains X part and Y part, then if you could define the task that you wanted to implement, no, if it is very precise, if both of them are clear, then no one can stop you, applying deep learning stuffs on them. Right. Let's move on. Right, and then in case if we decide, I guess there are 16 neurons in this first hidden layer. Yeah, 16. There are 16 neurons in the first hidden layer, and every input should be connected with all the neurons in the first hidden layer. So similarly, all the outputs of every neuron from the first hidden layer should be connected with all the neurons in the next higher hidden layer, and so on. So here this neural network configuration is also known as fully connected neural network. Okay, so fully connected in the sense, so every neuron in every layer is actually connected with every neuron in the other layer. Right? So that's the reason why we call it fully connected neural network. And in case of a fully connected neural network, the number of parameters that we are dealing with is going to be enormous. Okay? And then every neuron is also going to be connected with some bias. Okay, so bias will also be the parameter of the function, which must also be learned. Okay, so the learning algorithm will be guided appropriately in order to figure out, or in order to find tune the bias values as well. Okay, so for simplicity, bias B1 is actually connected with all the neurons in the first hidden layer, and bias B2 is connected with all the neurons in the second hidden layer, and then bias B3 is connected with all the neurons in the output layer. Right? As I told you before, if you do not have any clue on the weights, probably we could initialize them randomly, because every connections that we see, let's say a particular connection from X1 to this particular neuron, the first neuron in the first hidden layer, so this is going to come up with a weight value. So I have written it as a vector here, W1. So W1 actually is a vector whose size is actually it is going to be 16 cross 13. Yes, so this 16 denotes the number of neurons that we have in the first hidden layer, and this 13 denotes the number of inputs that we are dealing with. Okay, so the size of this W1 is going to be a vector containing these many values. So vector containing these many values, 16 cross 13. Okay, so you can also think of this W1 as a matrix of size 16 cross 13. So if you flatten the matrix, it becomes a vector, and whose size will be appropriately 16 cross 13. And then along with this, along with these many weights, we have bias value as well. So bias is also a vector whose size is going to be same as the number of neurons we have in the first hidden layer. Again, the size of B2 is going to be same as the number of neurons we have in the second hidden layer, and then size of B3 is going to be same as the number of neurons we have in the output layer. Okay? And let us see what happens at every neuron. So it is magnified here in this block diagram. So here at every neuron, we essentially perform two things. So one is, as you could see from this bigger neural network configuration, so every neuron actually receives input from all the neurons from the previous layer. So in case of the first hidden layer, so every neuron in this first hidden layer actually receives something from receives something from every input. And some of the connections are actually not done fully because if I do it, this diagram will not be readable. Just for the sake of just wanted to retain the readability of this neural network configuration. I just did not do several connections, especially if you could look at even this neuron should be connected with all the neurons in the second hidden layer. So similarly, X2 should be connected with all the neurons in the first hidden layer. X3 should be connected, X4 should be connected, and so on, which I have not done. Probably you could interpret it that way. Okay? Now, at every neuron, we perform two things, and one is the pre-activation, the other one is activation. So pre-activation is going to be computed as the weighted sum of all the inputs which comes from the previous layer. Okay? So the way how the weighted sum is going to be computed, in case the weights associated with all these incoming edges are from W1 to W1. Assume that I'm talking about this neuron. Just talking about this first neuron in the first hidden layer. So now this neuron, all the inputs from X1 to X13 are actually connected to this W1 along with this bias. Right now, the weighted sum could be computed as this weighted sum could be computed as like this. So it's going to be computed as Wi xi. So in case if the number of features are known to be 1 to 13, the I will be ranging from 1 to 13, and Wi xi plus bi. So this is what the pre-activation is all about, which we call it A. So A is going to be computed this way, and once you compute this value, and if you compute this complete thing, and A will be now a real value, and on top of it you apply some non-linear activation. Okay? The choice of H, H is again H is a function. We call it activation function. So we have several choices for activation function. It could be sigmoid activation, could be sigmoid activation, or it could be tan H, or it could be ReLU, or it could be leaky ReLU, and whatever. Again, as I told you before, it is in a hyperparameter tuning, and no one can tell you that sigmoid is a good choice, or tan H is a good choice, or ReLU is a good choice. And even though tan H and ReLU is most widely used in the context of deep neural network, so nothing wrong in trying out both of them. Okay, you have one configuration where you try out tan H at every neuron, or you have another configuration where you try out the ReLU, you have another configuration, similar configuration, you try out sigmoid there, and then you see if there is any improvement. Okay, and as you apply non-linearity on top of this pre-activation, then again the resulting value from this neuron is going to be a real value. So that real value is now going to be supplied to the subsequent higher layers. So again, at this particular neuron, so again here the pre-activation will be computed as the weighted sum of all the inputs which comes from the previous layer. So, but still, the output of this neuron still depends on all the inputs which are fed to this neural network. So that's the beauty, which means the input is involved at every neuron, not directly, but it actually passes through all the inputs, right? So inputs are actually fed here, and then the interpretation that we get at this neuron is actually depend on the input. So since the output of this neuron depends on this input, so definitely output of this neuron also depends on all the inputs which are fed to the neuron. So we do the same thing at multiple times. So you may think that the implementation may be complex, but we have well-defined libraries available. We have something known as PyTorch, we have TensorFlow, Keras, and so on and so forth. And those libraries actually will conceal most of the hidden implementation details, and you'll be able to implement. Probably, if you transform this diagram into an implementation in Python, let's say by using Keras or TensorFlow or PyTorch, so you'll be able to write this or design this neural network configuration in a matter of 3 to 4 lines. Okay, so it is that simple. So that's the reason why it's not going to be a difficult thing for us to try out multiple neural network configurations, so that you'll be able to better approximate the relationship between X's and Y. Okay, so that's fine. And coming to the output layer, okay, so the same thing is going to be done at every neuron. And one more clue is that, and if we decide to apply, let's say, sigmoid neuron, so it's a good practice to apply sigmoid on every neuron. Okay? So it is not that you apply sigmoid here and then you apply tanh here or relu here and so on. So that's not going to be good practice. And if you decide to apply sigmoid, and better to apply sigmoid all across the neurons, part of your neural net configuration. Okay. And then we have two neurons in the output layer, and as I told you before, it's a binary class classification problem. So you are going to determine your output based on the values produced by these two neurons. Now, again assume that we apply same reactivation here, which is going to be reactivation. This A3 part is going to be computed as weighted sum of all the outputs, all the inputs from the previous layer, right? And then we are going to apply, let's say, some activation on top of that. So it's going to return some real value, and this is also going to return some real value. And the real value is going to be ranging from no, it doesn't have any range. It could be anything. It could be anything. But in order to interpret this output for binary classification task, we supposed to have the output from the output layer, which is exhibited, which is represented in terms of probability value. So because we want to represent the output values in terms of probability distribution, so we do something known as softmax. So if you apply softmax on top of output, whatever output you get from the output layer, you apply softmax on top of that. And once you apply softmax on top of that, and the softmax is going to give you a probability distribution. So that in case if the probability distribution in the sense, you will get two values, and when you sum both of them, let's say the first neuron actually gets the probability value 0.9, and the second probability value should be 0.1. So when you sum both of them, it should be equal to 1. Okay, so now it's very obvious that because the probability mass is more on the first class, then it is very you can be sure that this particular data point should be classified with, let's say, label 1, but not with label 2, because label 2 is just only 10%. It is probable that it may be label 2, but it is 90% confident that it must be label 1. Label 1 in the sense heart disease, should be diagnosed with the heart disease or not. So you can appropriately interpret this probability value. Depends on the task that you're trying to solve. Okay, so the softmax is going to be computed like this. So it's going to be a very simple exponentiation function, and it is just to transform this output of these two neurons to a probability distribution value. So that's it. All the computations we see here are going to be very, very simple. And this is the activation function that that is actually applied on all the neurons in this particular neural network configuration, which is sigmoid activation. Okay. And then since we are dealing with probability distribution here, so we cannot use the square difference as loss function. So we're supposed to use some other loss function, so which is compatible with probability value. Okay. So the one of the choices we have, which is compatible with probability distribution, which is cross entropy loss. Again, all these equations are given, and you could even work out all these equations in pen and paper. So if you take a very small instance, so you will still be able to apply all this, but I'm not going to show you the way how we can actually apply these equations, and how are we actually arriving at all these equations. Okay? So even proofs are also going to be very, very simple, and the way how you can actually make use of these functions are also very, very simple. And actually coming to coding, so you need not actually look at these equations at all. So you just simply specify what is the last function that you want to use, and then you just simply feed the output from the output layer, and it will do everything. Right. So again, depends on the way how we interpret the output. So we use this cross entropy loss in order to compare the true distribution with the predicted distribution. Okay. So assume that the true distribution will actually look like this. It will be 1, 0, which means true label says that this particular patient record is actually diagnosed with heart disease. So that's why it is the entire probability mass is on the first label, and then there is no probability mass on the second label. And your prediction should also be, the ideal prediction should also be 1, 0, but not that may not be possible at all the case. That may not be possible most of the case. So assume that you arrive at these two probabilities. 0.9 in place of first label and then 0.1 in place of second label. And now you want to compare these two probability distributions. So in order to compare these two probability distributions, you can stick to cross entropy laws. The cross entropy loss will give you a real number which indicates the loss that your model is making or the error that your model is making. And again, ideally, this error should be as close to the zero. Okay, in case if the cross entropy loss is close to zero, then that's the loss that you're interested in. You can stop learning there, and you can decide to have the weight values which are used at that particular iteration and use it for making predictions on the unseen data. Again, the way how the learning algorithm is going to be used. Again, the way how the learning algorithm is going to change or update the weight values. So it is going to be it's going to update the weight values based on something known as um, no, derivatives. uh, I don't think I should be able to get into that part. I'll just give you a small clue the way how a particular weight in the neural network configuration is going to be updated. Okay. So the way how we are going to update, let us see how weight update takes place for this weight. Assume that I initialized at random. So now after the complete run of one epoch, I would be getting the loss at the output layer, and depends on the loss, I supposed to change each of the weights involved in this neural network. So, and coming to this particular weight, the way how it can be adjusted, assume that I am now trying to update weight 1 1. So the old weight is going to be updated as new weight. It's going to be actually updated by don't ask me why do I use minus here. It's up to you. You could even use plus here, okay? Because we are actually skipping a lot of technical details here. And but nothing wrong. You could either use plus or minus. The only thing is we want to update this particular weight so that it would make change in the loss, or it would make some reduction in the loss. Okay? The change is again not random, so change is going to be done based on the choice of learning algorithms we have. As I told you before, we are going to make use of some flavors of gradient descent algorithm, and gradient descent algorithm will always guarantee that when there is update takes place on every weight used in the neural network, and definitely there will be reduction in the loss. Okay, so that's how the gradient descent actually updates the weight value. So it does not do it at random. So it actually do it systematically so that there will be reduction in loss at every epoch or every run of the every run over the data set. Right? And then it's going to be updated as the old value. The new value of W11 is going to be updated as the old value plus eta times. So this eta is going to be a learning rate. So how fast you want to update this W11? So again, this learning rate is an hyperparameter. So generally this learning rate should be as smaller as possible. We generally put it like this 0.001 or 0.1 and so on. Again, it's a hyperparameter. You will have to try out different learning rate, and then you decide which one helps you to converge the learning faster. And then the derivative of the loss function with respect to this particular weight W1. Okay? So the derivative of the loss function in the sense, so actually this loss is actually contributed by the weight, right? So now if I want to change this loss, I supposed to change this weight. So that's what this this portion derivative of the loss function with respect to W11. So similarly, I should do it for all the weights that you see, all the arrowheads that you see. And if you could measure the number of parameters involved in this neural network, and you could simply count all the arrowheads that you see here. So as I told you before, the size of W1 is 16 cross 13 because we have 13 neurons in the first hidden layer and then 13 input values. Okay, and then plus the number of biases. The number of biases we have is again 16, which depends on the number of neurons we have in the first hidden layer. Again, coming to W2, the size of W2 is going to be 16 cross 16 is the number of, or let me write it 8 cross 16. 8 is the number of neurons we have in the second hidden layer, and then we have 16 neurons in the first hidden layer. and plus the number of biases. Number of biases is equal to the number of neurons we have in the second hidden layer, okay, which is 8. Again, coming to this layer, again the number of weight values or number of parameters involved here is it's going to be 2 into number of neurons in the second hidden layer. 2 denotes the number of neurons in the output layer plus the number of biases, which is 2. So sum all of them. So this one, and this one. So if you sum all of them, that's the number of parameters that we're dealing with. So you will have to apply this update rule. You will have to update this. You will have to apply this update rule for all the weights that you see in this deep neural. Again, you need not do it, or you need not write code for every update. You need not use for loop or anything, in order to repeat this task. And again, libraries will guide you in order to do it so precisely. Yeah, moreover, the way how they implement this update rule, moreover, is going to be very, very efficient. So if we hard code it, we may not be able to give that efficient implementation for this update rule. But the libraries like PyTorch, Keras, TensorFlow, they actually provide very good implementation for each of these update rules, so that when you run this neural network on any data, you will be able to see it works very fast. So in case if you're dealing with very huge amount of data, probably you could even make use of GPUs in order to speed up the process. Okay? You can get support from specialized hardware, which may help you to run or converge the learning at the earliest. These are the various strategies to improve deep neural network. And why just stick to gradient descent? Why not momentum based or accelerated gradient descent or ARAGRAD or RMS or again, you could use them in 3 different flavors. So this actually tells the way how you update the weight. So how frequently you update the weight. Just by looking at a single instance, you update it, or you look at the entire data set and then update it, or you look at a batch of some specific size and then you update the weight. And then why you need to initialize the weights at random? Why don't you use some good strategy to initialize? So there are some good strategies to initialize weight values for a deep, which is proposed by Xavier and he. They proposed a very good initialization method so that your learning algorithm will work well. Okay, so it will be interoperable. So if you initialize them using these strategies, so the convergence will occur, and then you have different choices of activation functions. You have something known as regularization, because as and when the function becomes complex and complex, so it is actually prone to overfit. Okay? So we have a problem of overfitting in the context of deep neural network. So in order to avoid overfitting, we use this regularization. Okay? So overfitting is all about if your model simply memorizes the learning data or training data. So we don't want the model to simply memorize the training data. We want model to approximate the relationship between X and Y, which means we want it to learn something, not just by heart or simply recollect what is present in the training data. Okay? So that property is what called as overfitting. So in order to avoid it, we have several approaches to carry out. So all these are optional techniques, but all of them are very popular too in the context of deep neural network. And you can have something known as dropout, data augmentation. In case if you deal with less amount of data, it is very prone to overfit. Okay, if you have very little amount of data, your complex deep neural network model would simply memorize it. We don't want that to happen, so you could augment data, or you could stop. You could early stop the learning. Maybe you may have pre-decided to run, let's say, 1,000 epochs or 10,000 epochs, but at the end of 500 epoch, there would be very good set of parameter values you might have obtained. So why should you carry out the remaining epochs? You just stop there itself, and then you just stop the learning, and then you decide the parameter values. And then we have something known as regularization. Again, regularization is applied in order to avoid overfitting, which means you don't just update the weight value. So along with that, you also update the other. You also, which means, let me not get into the details of regularization. Regularization is all of. We don't want to minimize loss alone, so we want to even minimize the other factor as well. Okay, so that additional factor is what actually called as regularization term. So we would even be careful with that regularization term as well, in order to avoid model being old. So even if you further extend it to CNN or RNN or LSTMs, all the internal stuffs are going to be the learning algorithms, initialization technique, activation functions, and then regulation. Okay, these stuffs are not going to be changed even in CNN or also. So the way how we deal with data representation may be different in CNN and RNN, but the choice of these hyperparameters are still going to be same even CNN, RNNs, and other flavors of neural network techniques. So let me straight away go to the application areas and let us see what we could do by using deep neural network on this drug discovery. So meantime, let me just read out few questions which are there in the chat. I want to just know whether this is applicable to pharma. No, definitely not, sir. It is not only on pharma industry, and anywhere you have data which is compatible, where you can apply deep learning, you can apply. So deep learning is widely applied in financial domain and widely applied in insurance. So it's applied everywhere. Even in HR, it is applied. So even the HR department in an organization, so they do a lot of they do apply learning algorithms, to know, who will turn up for joining, who will not turn up for joining, and so on. And it's deterministic models. Yeah, these are all deterministic models, which means it is bound to certain things. Let's say if to understand the neural network of supply chain of MCG industry, can I use? Yeah, definitely you can do it. Supply chain. There are a lot of applications you can find in supply chain, as I told you before, even in human resources as well. Right. So I've gathered a lot of applications under drug discovery, but I'll spend more time on deep learning itself. But anyhow, it is good to go because as long as you find data which is in the form of X and Y in the context of drug discovery, so with no doubt you can apply deep learning. Right. So the earlier the drug discovery was completely serendipity, which means out of surprise they were able to discover a lot of drugs. And you can again explore over internet and you can find out what are those surprise researches which resulted in very good discovery of drugs. So serendipitous in the sense, out of surprise, they do something, but they get something. So they were trying to do something, but as a result of that activity, it resulted in a very good medicine. So which healed a lot of people in the past. Okay, so you could figure out what are those serendipitous researches in medical field, and there are a lot of such serendipity things that we can observe in chemistry and chemical sciences. And let me go to the data set directly. So you could figure out these two data sets, particularly the first one on Kaggle, so which is about MOA annotations for more than 5,000 drugs. So MOA annotations in the sense, so for each of these 5,000 drugs, what is the change that happens in the human body? So that is what is denoted by MOA annotations. MOA in the sense it is mechanism of action. So upon taking some medication, so what changes actually happens in the human body? So what changes happens in the human body? So that is actually going to be denoted with a very good set of features. I think the size of this data set is very huge. I think I counted the number of columns in the data set is about 800 plus. So it's really good in number. So with no doubt, you can still apply some learning on top of it, which means as you make changes in the drug, so what changes actually happens in MOA annotations. So they have given you a training data which contains both drugs as well as MOA annotations, so that you can definitely be able to learn the relationship between the drug and the MOA annotations. Okay, which means the chemicals, drugs are actually expressed by some chemical substance. Again, drug is not just denoted by a name of the drug, so it is actually denoted by some the chemical compounds. So it is not just done explained by a matter of one or two values. So every drug is actually explained by hundreds of values. Similarly, every MOA annotations are actually described by hundreds of values, several hundreds of values, so that there is a good scope, for learning the relationship between MOA annotations and the drug that we have. Okay, so even there is one more data set on COVID as well. So they have given gene expression data for COVID patients along with some prescribed medications. So the reason why we apply deep learning here, so a lot of chemical trials and chemical the laboratory tests could be gradually decreased, because the major problem that we have in the context of drug discovery is that so drug discovery is a very tedious process and expensive process, and we may have to repeat same thing for several times. And moreover, it is a fact that in order to release a medication or in order to release a drug in the market, so they're supposed to do about a 10-year of activity there, and they have to invest lots and lots of money on them, in order to finally release the drug in the, okay? Which means they have enormous possibility of chemical compounds that's supposed to be explored. Okay, so trying out all possibilities is not going to be that easy. So they say that the number of possibilities they have for various chemical compositions are actually close to 10 power 60. Okay, so the field of computer science struggles for this number actually, for 2 power 64. Uh, even a modern computer would fail or would even fear at this number 2 power 64. So what is this number? 10 power 60 is very very huge than this number. So we have such vast range of chemical compounds that we have, and exploring all of them and figuring out drug for a disease is a very very challenging task. Okay, so far they were doing manually, and they were doing a lot of chemical they were doing a lot of laboratory tests in order to discover a drug. But what this deep learning stuff can actually supplement this by accelerating this process. It can speed up this process so that it can even reduce the cost involved in this process. Instead of taking 10 years of time to release a drug in the market, probably if wherever possible, if we take advantage from deep learning, probably we could do it in the matter of 1 year or 2 years, because a lot of data crunching process could be taken care by deep learning, so that the lot of search and explorations on the possible chemical compositions we have. So the deep learning can converge faster, and it can give you reasonable results at intermediate level, which can accelerate this entire drug discovery and development process. Okay. So again, I put a mystery here. You can explore offline why computer fear at this number 2 power 64. There are some interesting stories behind this number. Anyhow, if you are from computer science background, probably you would be aware of this number. Why this 2 power 64 is a very dangerous number for in case if 2 power 64 is a dangerous number, what about this 10 power 60? So there comes the notion of deep learning and all that, where we are going to do a lot of approximations, randomizations. Okay, if possible, even heuristics can be applied. So thereby, so it would collectively get some insights from such a large universe of chemical compositions. Again, you can think of a lot of classification tasks and regression tasks on this data. So this data is completely numeric, and so you can think of several classifications. You can classify drugs into various categories, or you can given a drug, you can find out what would be the MOA annotations. So why should you give a drug? Why should you, give a drug to a patient or a person who is under test or under experimentation, and then you read the several readings from the human body, and then you represent the MOA annotations. Okay? So if you could automate this task, so you have this huge data set with you. So why can't you do it for a new drug, for a given drug? So can you model, or can you come up with an MOA annotations? Okay? MOA annotations in the sense how human body reacts for a drug. Okay? You have already trained a model with 5,000 drugs on various MOA annotations. So can you make use of the model, so in order to find out MOA annotations for a new drug? And that could be possibly one direction considered. And then drug target prediction. Okay? So given a drug, so which among these MOA annotations are useful? So MOA annotations are, as I told you before, it is expressed by hundreds of attributes. So among hundreds of attributes, some of the targets would be more influential. Right? So not all human body cells are going to be reacted for every drug. So some of them are going to be very active for some of the drugs. So can you predict them? So what are the cells or the what are the substances in human body so reacts for a given drug? So that is one direction. Again, where deep learning can help you to model this problem. Again, as I told you before, probing the compound space. So the size of the compound space is actually sorry, 10 power 60, sorry, 10 power 60. And again, probing or searching some meaningful compound composition from this vast collection is a challenging task. Okay. So again, for which there is a data available, which contains something called as Smiles representation. So Smiles representation in the sense the chemical compounds are actually represented in terms of Smiles notation, so that it can be stored in computer and computer can process it. So if computer can process, definitely a deep neural network can also process it. Okay. An example, I think I had an example somewhere. Yeah, here is the Smiles representation. This is the Smiles representation for this particular chemical compound. So if you know what DFS algorithm is all about, depth first search algorithm, so they just they take a substance and they run a DFS algorithm on this graph because they, computer point of view, we just visualize this chemical compound as a graph and on which we apply DFS so that we get to see different paths here and each of them are actually translated to some sort of coding. So you will have to remember and recollect several coding schemes. There is a coding book even available online. If you wanted to know how this chemical compound is represented in terms of Smiles notation like this. So if you want to know it, probably you can explore the documentation and you can understand how it is done. If not, so if you are just interested in this alone, this data is straight away available. Okay? So again, for this particular chemical compound, how the genetics, human genetics, react. That data set is also available again on Kaggle. Again, you can make some changes to it. So what changes? If you make some changes to it, what is going to be the adverse effect on the human biology? So these are some of the places where deep neural network can be used, so that you can find out the relationship between two things. Two things in the sense input and output. So it is up to you to decide what are you going to treat as input and what are you going to treat as output. Okay. So once you choose what is going to be the input and output, then that actually defines the task explicitly. So with this, let me conclude my talk. Probably I'm now ready to take up some questions from the audience. Yes, there are no questions from the participants. Probably over to the organizers.
Participants, if you have any queries, please do raise it.
The drug discovery itself could be treated as a possible direction. There are a lot of scope and very least amount of work has been done. Because even for this task, I have gone through several papers which are actually published in medical journals and bioinformatics related journals. But still, there is a lot of scope for applying this type of computational techniques on this type of data, drug discovery related data.
Sir, hello, can you hear me, sir?
Yeah, yes, ma'am.
Thank you for your very informative lecture on deep learning. So actually, I have a question on drug discovery. So you told us that DFS algorithm is utilized for
Yeah,
drug
that
discovery.
is just to represent the chemical compound. That's it.
So is there any other algorithm available for representing a chemical?
Because if DFS is possible, definitely BFS could also be possible. Probably the way how we represent this Smiles notation could be different, but that could be one other way to do it. But madam, can I know why are you interested in representing it? Because already the representations are readily available for thousands and millions of chemical compounds. Probably you could straight away work on them.
No, sir, I just want to create my own database. So for that,
Okay. And the one thing that I noted, because which is recently getting popularized, that is Smiles notation. But I did not get any other representation. Possibly there would be some other representation.
thank you.
Okay. Sir, I have a question. Hello, can you hear me, sir?
Yeah, yes, please.
Okay. Sir, I have gone through this precision medicine thing. But there's one thing like gene editing, right? So
Yes.
the bioinformaticians, they are using the CRISPR-Cas9. And can we do it in deep learning algorithms, using the deep learning algorithms?
Yeah, even one of the data sets which I spoke about, this one,
Yeah.
this MOA annotations. So in these MOA
Okay.
annotations, uh, the reaction in the human cell for a drug is actually represented in terms of gene expressions. I just
Okay.
simply put forth as MOA annotations. This MOA annotations is nothing but the gene expression. Yeah. So there is a
Okay,
lot
sir.
of scope because gene
Okay.
expression. But what would you like to do with the gene expression?
So I'm just concentrating this precision medicine thing. So
Okay.
genome
So one,
sequencing and actually I'm a computer science engineer and it's hard for me to understand the terms of the bioinformatics.
there is a good scope there in the and one thing that you could do, uh, say
Yeah.
for example, the gene expression data is available for every drug. So
Okay. Okay.
when we inspect a drug, when we provide a drug to a patient or a person
Okay.
who is under
Okay.
experiment, and whose gene expression is also readily available, which means we have a pair of
Okay.
drug and then gene expression, so that you can try to figure
Okay.
out for a given drug, uh, what would
Okay.
be the change in the gene expression. That is possible with deep learning.
Okay. Okay. So with the normal like Google Colab or something we can do it, right?
Yeah, you can implement it in anywhere. Yeah,
Okay. 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 Is there any particular libraries we can use?
this PyTorch you can use, and then there is
Okay.
one more library which I don't remember. They actually, it is written in Python, and it is explicitly available
Okay.
for MOE annotations. Because
Okay.
over MOE annotations, we would do something very frequently, for which
Okay.
some special library is readily available, which I don't recollect.
Okay.
It is something like
Okay.
PyChem or something, PYCHEM. I don't remember exactly. So it
Okay.
has a
Okay.
lot of libraries to work with chemical compound representations.
Okay, sir. Okay,
Yes,
thank you.
yes. Thank you.
Any other queries from? Thank you so much, sir. This was an outfight with your great answers. Thank you so much, sir.
Yeah, thank
The
you.
feedback for particular.
Yeah, you can apply drug discovery. You can apply ML on drug discovery, but ML has very restricted functions. So as I told you, as part of this talk, I told you that our main objective is to approximate the relationship between X and Y. So the way how we do it by coming up with some neural network configuration, which is a model. But ML, if it is very specific, it depends on the task that you have. Again, drug discovery is a very big umbrella, so under which we have several regression, classification tasks. Probably, if it is regression or classification, definitely you can apply ML. Not necessarily you must apply deep learning, but deep learning is also another class of algorithms we have. Because in the recent days, we observe that deep learning gives better performance in terms of modeling. So in case if you could do it by using ML itself, it is well and yes. Thank you. Yes, if there are no more questions, I thank the organizers for having invited me for this task, and I thank all the participants for your patient listening. And over to the organizers. And I'll take a leave time.
Thank you, Wellington, sir, for your nice presentation.
Yeah, thank you, madam.
Thank you, sir. Thank you so much.
Thank you so much.
Dr. Winston. Dr. Winston.
Yeah. Oh, sir.
Hello.
Balamurugan, sir. How are you?
I'm Ganesh
Good evening, sir.
Balamurugan. Can you hear me? How are you, sir?
Yeah,
நல்லா
sir, I
இருக்கேன்
know,
சார். ரொம்ப
yeah,
தேங்க்ஸ் சார்
I could
உங்களோட
recollect.
இன்விடேஷன்
How are you,
அக்செப்ட்
sir?
நான் நல்லா இருக்கேன் சார்.
Okay, sir. சொன்னாங்க சார், மேடம் சொன்னாங்க.
நம்ம
ஓகே ஓகே.
தேங்க்யூ சார். தேங்க்யூ வெரி மச் சார்.
சார்.
உங்களுக்கு அப்புறமா கால் பண்றேன்.
தேங்க் யூ சார். தேங்க் ஃபார் ரெக்கமெண்டிங் மை நேம் திஸ் டாக். கண்டிப்பா சார், கண்டிப்பா பேசலாம். தேங்க் யூ சார். Madam, can I leave the meeting?
Sir, can't hear you, sir.
Yeah, can you hear me, ma'am, now?
Yes, sir. You're audible, sir.
Yeah, ma'am. Can I leave or I think
Yes, sir.
probably the next
Yes, sir.
session
You
will
can
continue
leave.
now.
Yes. No, sir. No, sir. You can leave the session, sir. The next session will be scheduled. That will be around 2 o'clock, sir.
Okay. Yeah. Please
Okay.
give this to participants. Yeah, thank you, ma'am. Thank you.
Thank you so much, sir.